Alright, this is Honors Geo, Chapter 5, Section 2, Perpendicular Bisectors. Alright, so recall that a perpendicular bisector is a line, point, segment that cuts something completely in half. So you have AB, and then we have this line. Let's call it C, and it intersects AB at P, such that it does two things. It creates perpendicular angles, and it cuts AB in half. So this is a perpendicular bisector, if you recall. So let's just call it this, perpendicular bisector. Does two things. Well, it can either be a ray, line, segment, or point. I guess it could also be a plane. And it does two things. Cuts it in half. And it creates a perpendicular intersection. With that information in mind, we have something called a perpendicular bisector theorem. And what happens is that if I know I have a perpendicular bisector, and I know that there's a line, a point on that perpendicular bisector, this point C, if I was to connect a point here and a point here from the perpendicular bisector, then I can say that from that point to the end of the segment, these guys are equidistant. Equidistant meaning they're the same distance. So if I have a perpendicular bisector, so if I have a line CP and it's the perpendicular bisector of AB, then I can say that any point on that perpendicular bisector will be equidistant from the endpoints. So then CA is equal to CB. Notice it doesn't say congruent. It says equal. So we use this in proofs. Usually we have proofs that say that their stuff are congruent. In this case, we have stuff that says that they're equal. Meaning we can sort of eliminate that step when we use it in a proof, which is nice. Now it's not just point C, it's any point along this perpendicular bisector. So let's say I had a point X, and if I was to draw a line from A to X and B to X, then I can say that AX is equal to BX. Or if I had a point higher, point Z, I was to draw a point from here to here. One, two. This would be 4. then I can also say that ZA is equal to ZB. Any point along that perpendicular bisector, if I draw a line from there to the end of the two segments that is bisecting, those guys will always be congruent. Perpendicular bisector theorem. Yep. I can also get a converse out of that. So let's say I have a line, again line CB. Let's see, now let's make my segment. We have segment AB, lac befell. I have a perpendicular bisector, again, at CP. It cuts it in half. I have some other point, and the book calls it point D, such that when I connect the end segments to it in space, it is congruent to each other. But I'm not sure quite yet if it lies on the perpendicular bisector, because the line doesn't extend out. So this is the perpendicular bisector converse. And what this guy says is the opposite of the perpendicular bisector. If this is point D, if AD is equal to BD, then I can say that point D is on the perpendicular bisector. And it's on a perpendicular bisector of the segment. In this case, segment AB. Okay, so the reverse is true. If there is some point such that it's equidistant from both end segments, endpoints, then it is the perpendicular bisector, or it lies on the line, which is the perpendicular bisector of said segment. Okay. So here, algebraically, pretty straightforward. They tell me it's a perpendicular bisector. Since I know it's a perpendicular bisector, then I can set these two sides equal to each other and solve for the variable. So here we have this scenario here. We have 25 and 25 at point V. We have WX, and we're told that WX is the perpendicular bisector of XZ, YZ. What's the segment lengths in the diagram that are equal? WY is it's not a segment. WY is equal to WZ based off of the perpendicular bisector theorem. And then we also have that YV is equal to ZV, and that's because it's given to us. Then part B says since they're equidistant from Y and Z, then the converse must be true. That V is on the perpendicular bisector. So here we go. Here, what is the segment lengths that are equal? Here we have, we're told that it's a perpendicular bisector, so NK is equal to LK. We have NM is equal to ML. they want you to find NK. So since they are the perpendicular bisector, then I know they're equidistant from each other, so it's going to be 6x minus 5 equals 4x plus 1. That's going to be 2x equals 6, x equals 3. Plug it back into either one, doesn't matter. 6 times 3 minus 5 is 18 minus 5, which is 13. Or if you did 4 times 3 plus 1, that's 12 plus 1, which would be 13. Either one works. So NK is 13. Explain why M is on the perpendicular bisector. The converse of the perpendicular bisector says that if M is equidistant from the end segments, then it lies on the perpendicular bisector. So converse. Perpendicular bisector theorem. All right, concurrency. Concurrency. That is when 3 or more lines, rays, or segments intersect. 3 or more lines, rays, or segments intersect. That's called concurrency. Point of concurrency is the intersection point of those lines. So the intersection point of 3 or more lines, rays, or segments. Okay. All right. So when we talk about point of concurrencies within a triangle, or point of concurrency of perpendicular bisectors of a triangle, we have a unique rule. And the unique rule is this. If we have a triangle, I feel like I've been saying that a lot lately. If we have a triangle, and this triangle A, B, and C, and this triangle has 3 perpendicular bisectors. Now y'all know this is not going to be to scale at all. I am eyeballing this son of a gun. Definitely eyeballing this bad boy. Now, this is just an educated guess where this guy is. We call this point P. All right. We have D, E, and F. All right. They are perpendicular bisectors, right? So it's going to be perpendicular here, perpendicular here, perpendicular here. They're going to cut it in half, cut it in half, cut it in half, cut it in half. So we have 3 perpendicular bisectors. The point of concurrency is at point P. And what the concurrency of perpendicular bisectors of a triangle theorem says is that if I have a point of concurrency of the perpendicular bisector of 3 triangles, if I was to create a line, from that point of concurrency to the vertices or to the vertex of each triangle. And again, not to scale. Then those three lines, the yellow lines, would be congruent. So this guy, and this guy are all the same. And I put them in blue to differentiate. These guys would be congruent to each other. So if P D, P E, and P F are perpendicular bisectors, then, and that falls in line with the perpendicular bisector theorem, right? If it lies on the line of the perpendicular bisector, then any point for the end segments must be congruent, right? So this is just an extension of the perpendicular bisector as it applies to triangles. Then PA is equal to PB is equal to PC. And that's that long ass, the name of this theorem. So concurrency of perpendicular bisectors of a triangle theorem. It's a long name, or theorem 5.4. And again, if I have the perpendicular, if point P is the intersection of three perpendicular bisectors in a triangle, then that intersection point is equidistant across the vertices of the other triangles. Perpendicular bisector of a triangle intersect at a point that is equidistant from the vertices of a triangle. Okay. I'm not going to do that one because I don't feel like drawing it more. It's basically asking me to draw the same thing that I did there. Circumcenters. The point of concurrency of a perpendicular bisectors of a triangle is called the circumcenter. So option POC, point of concurrency of three perpendicular bisectors of a triangle is called a circumcenter. Okay, we have three types of circumcenters. The one that we've been dealing with primarily is when the triangle is an acute triangle. I'm not going to draw these. But when there's an acute triangle, the equidistant points are going to be inside there to each vertices. When we have a right triangle, the right triangle, so this is circumscribed, meaning the triangle is being, has a circle drawn around it such that the circle hits at each endpoint of the triangle. So this triangle is being circumscribed. And when it's an acute triangle, point P is actually the radius of the circle at the same time. And when it's an acute triangle, the line from the segment from point P to the endpoint all represent actually the radius, in addition to the fact that it represents the line that is equidistant from that point to the vertices. In a right triangle, Again, point P would be the center of the circle, and the point of concurrency, the circumcenter of the triangle. And when it's a right triangle, it actually meets up at the hypotenuse of the triangle. And the distance from P to that vertex is the same as distance from P to that vertex, and it's the same as distance from P to the right angle. And again, they all are also the radius of the circle. So it's the radius of the circle and the point of uh, concurrency of this triangle, or in this case, the circumcenter, which is the same thing. When we have an obtuse triangle, the point of concurrency is on outside of the triangle. Again, a radius of the circle. This line goes through is the perpendicular bisector of this triangle. This line is the perpendicular bisector of this triangle, and this line is the perpendicular bisector of that triangle. And as they meet, as you draw the line through the circle, they meet on the outside. All right. So the circumcenter, or point of concurrency of a perpendicular bisector, is on the outside of an obtuse. It lies on the right triangle, usually the hypotenuse of a right triangle, and it is in the center, or inside of the triangle in an acute triangle. Okay? So, that is that section. I hope you have a great rest of your day.